Okay, so that's how fast an individual wave crest travels. But if you're a surfer, or even if you've been down the beach and just watched the waves roll in, you'll know that waves usually come in things that surfers like to call sets, or if you're a physicist, you would call a group. Okay, so a wave comes in a group. And there's this interesting property that a group of waves travels at a different speed to the individual wave crests. And so how does that work? Well, you can imagine you have this group of waves propagating here. So each of these individual waves is traveling at that phase speed that we figured out. But there's these 4 waves in the group. And what you'll find if you watch these things is the wave 1 will gradually die out, but a new wave will form at the back. And it keeps moving, and then the second wave dies out, and another wave forms at the back, and so on and so forth. So the waves at the front vanish, and the waves at the back, and the new waves form at the back. And so this is actually because the wave group travels half as fast as the individual waves. Why is this? So to understand this, we actually have to think about the fact that our waves propagating on the ocean are not just one wave number and one frequency. They're actually a superposition of a few different wave numbers and frequencies all piled on top of each other. Usually we think of it as a wave group being composed of a small band of wave numbers. And we represent this as something called a spectrum. So that's, if we can draw that as an amplitude of waves as a function of k, and there's just some amplitude that varies with k. And that is peaked around the reference wave number for that group, which is this k0, and it has some narrow width around that. And the total sea surface amplitude from all these waves is just the sum over all those different wave numbers. So let's think about this in a very simple way by saying, well, let's have 2 different waves which are near this wave number. We're going to pick one that's going to be k minus some delta k here, k minus delta k, k0 minus delta k, and we'll have another wave that's here, k0 plus delta k. Okay, and we're going to assume our group is just a combination of those 2 waves. So let's write down the waveform for each of those. So you can see that down here. We've added up a k minus delta k and a k plus delta k. And we can expand those things out. So this frequency at k minus delta k, we can approximate as the frequency at k0 plus the change in frequency with wave number by the change in wave number delta k. So this is just a linear expansion of the dispersion relation, this function omega of k. And so if you plug that in here for omega k minus delta k and omega k plus delta k, and remember some of your trig identities, you can show, it's a good exercise for you, you can show that this comes out in this form here. And so it becomes a product of 2 different sinusoidal functions with a double amplitude. So at the front here, you've just got your normal continuous wave structure at your wave number k0. But modulating that, you have this other sinusoidal function, which is at a much smaller wave number of delta k. And this is actually the envelope of the wave group.
If we make a movie of what this function looks like in time, you can see the individual wavelength propagating through the picture, but being modulated by this wave envelope. And if you look closely, you can see that these individual finer waves are propagating faster than the envelope. And so exactly as we argued in the schematic to the right, the waves gradually die out at the front and grow at the back of the envelope over time.
Using the same approach we had before, we can think about, well, what is the speed of this wave group? So if the wave group is this second cos here, then again, let's take a time derivative of the phase of that as as shown here and apply the same argument as before, we're going to find that dx dt is equal to this d omega decay. So the rate at which the wave envelope propagates is d omega decay. And we call this the group speed, or c sub g, of the wave. Now, for the surface wave, so again, up to this point has been entirely generic. This applies for any type of wave. But now if we think specifically about the surface waves in deep water, we know that our frequency was the square root of gk. Okay, so given this dispersion relation, we can write down the group speed is d omega on k, which we can calculate that derivative. It's 1/2 square root g on k. And if you look at that closely, you'll see that that is actually just omega divided by 2k. And if you remember, the phase speed was omega on k. So here we've just got an expression which says that the group speed is half the phase speed. So in other words, the wave groups travel half as fast as the individual wave crests. Important to keep in mind that the group speed is because it's the speed at which the whole wave group travels, it also tells you about how fast the energy in those waves travel, because it's the whole collection of perturbations to the sea surface together are traveling at this speed, which means that's the speed at which the energy is moving.